Tonight, we're going to explore something that will fundamentally change how you understand reality itself. We're going to discover what space-time actually is, not as an abstract equation or a historical footnote, but as the actual fabric of existence. Because here's what most people don't realize. Space and time aren't two separate things that happen to coexist. They're one unified structure, and everything you've ever experienced, every moment of your life, every object you've ever touched, exists within it. And this structure has rules. It decides what can happen and what absolutely cannot. It determines cause and effect. It shapes gravity itself. By the end of this journey, you're going to understand why physicists say space-time is the stage on which reality performs, and why that stage is far stranger than you ever imagined. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe would really help the channel grow. It's a small thing for you, but it makes a huge difference for me. Make yourself comfortable. Let's begin. Let's start with something you already know, or at least something you think you know. Space and time. These seem like completely different things. Space is where things are. Time is when things happen. You can move through space in any direction you choose, forward, backward, left, right, up, down, but time seems to push you relentlessly in one direction only. Always forward, always at the same pace. You wake up in the morning and the day unfolds, whether you want it to or not. You can't go back to yesterday. You can't skip ahead to next week. Time just happens to you. Space feels different. Space feels controllable. You have choices about where you go. You can walk to the kitchen or stay on the couch. You can drive to another city or fly to another country. You can climb a mountain or descend into a valley. Space offers freedom, time offers none. And this distinction between space and time seems so fundamental, so obvious, so built into the structure of reality, that humans never questioned it for thousands of years. Ancient philosophers debated the nature of space, they debated the nature of time, but they always treated them as separate subjects, separate questions, separate mysteries requiring separate explanations. This intuition served us remarkably well, for everyday life, for building houses and planning trips and scheduling meetings. Thinking of space and time as separate works perfectly fine. You need to know where something is and when it will be there. Two different pieces of information, two different measurements. The address and the appointment time, the location and the schedule, completely separate. If someone asks you to meet them, you need both pieces of information. The coffee shop on Main Street, 3 o'clock on Tuesday, space tells you where to go, time tells you when to be there. These feel like fundamentally different kinds of information. One is about position, the other is about duration. They don't seem related in any deep way. This separation seemed so natural that it became embedded in how we think about everything. Physics, before the 20th century, treated space and time as independent quantities. You could measure distances with rulers and times with clocks, and the two measurements had nothing to do with each other. A meter was a meter whether you measured it quickly or slowly. A second was a second whether you were moving or standing still. But here's where things start to get strange. In the late 1800s, physicists began noticing problems. Not small problems. Not minor discrepancies that could be patched over with a bit of mathematical tweaking. Fundamental, reality-breaking problems that threatened to undermine everything they thought they understood about how the universe works. And these problems all centered on one thing: light. Light is electromagnetic radiation. It's waves of electric and magnetic fields traveling through space, oscillating back and forth as they propagate. When the Scottish physicist James Clerk Maxwell unified electricity and magnetism in the 1860s, his equations made a prediction. They said electromagnetic waves should travel at a specific speed, about 300,000 kilometers per second. This became known as the speed of light, often written as the letter C. This was a remarkable prediction. Maxwell's equations came from studying electric currents and magnetic fields in laboratories. They had nothing to do with light, or so people thought. But when you solve the equations, out popped this speed, and when scientists measured the speed of light, they found it matched Maxwell's prediction almost exactly. Light was electromagnetic radiation, one of the great unifications in the history of physics. But here's what was strange about Maxwell's equations. They didn't say the speed of light relative to what. Every other speed we know about is relative to something. When you say a car is going 100 kilometers per hour, you mean relative to the road. If you're in another car going 90 kilometers per hour in the same direction, the first car seems to be going only 10 kilometers per hour relative to you. Speeds add and subtract depending on your own motion. That's how velocity works. That's basic physics that had been understood since Galileo. So physicists expected light to work the same way. They thought there must be some medium, some substance that fills all of space through which light waves propagate. Just like sound waves travel through air and water waves travel through water, light waves must travel through something. They called this hypothetical substance the luminiferous ether. Light would travel at 300,000 kilometers per second relative to this ether. And Earth, moving through space in its orbit around the sun, would be moving through the ether too. So the speed of light should appear different depending on which direction you measure it. If you're moving through the ether toward a light source, the light should reach you faster. If you're moving away, it should reach you slower. Just like how the speed of sound appears different if you're moving toward or away from the source. In 1887, two American physicists named Albert Michelson and Edward Morley set out to measure this difference. Their experiment was incredibly precise. They used a device called an interferometer, which splits a beam of light and sends it along two perpendicular paths. The beams travel out, hit mirrors, and come back. Then the device recombines the beams. If light traveled at different speeds in different directions because of Earth's motion through the ether, the recombined beams would be slightly out of sync. They would create an interference pattern that would reveal the difference in travel times. The Michelson-Morley experiment was one of the most careful measurements in the history of science. They built their apparatus on a massive stone slab floating in a pool of mercury to eliminate vibrations. They repeated their measurements at different times of day and different times of year, when Earth's motion through space pointed in different directions. They were confident they would detect Earth's motion through the ether. The result shocked everyone. There was no difference. None at all. No matter which direction they measured, no matter what time of year, no matter how Earth was moving through space, light always traveled at exactly the same speed. The ether, if it existed, was completely undetectable, and light seemed to have a speed that was the same for everyone, regardless of how they were moving. This was deeply disturbing. It violated everything physicists thought they knew about motion. If you're on a train moving at 50 kilometers per hour and you throw a ball forward at 20 kilometers per hour, someone standing on the platform sees the ball moving at 70 kilometers per hour. The velocities add. That's basic physics that had worked perfectly for centuries. But light didn't follow this rule. Light from a flashlight on the moving train would reach the platform observer at exactly the same speed as light from a stationary flashlight, 300,000 kilometers per second. Not 300,000 plus 50, not 300,000 plus anything, just 300,000. Always. No matter how fast the train was moving, no matter how fast you were moving when you measured it, various physicists proposed solutions. The Dutch physicist Hendrik Lorentz developed mathematical equations describing how lengths and times would have to change to explain the null result. The French mathematician Henri Poincaré recognized that these transformations had deep significance and even spoke of a principle of relativity. George Fitzgerald in Ireland proposed that objects physically contract when moving through the ether. These ideas helped save the appearances, but they were awkward. They felt like patches applied to a wounded theory, rather than genuine explanations. The ether remained, invisible and undetectable, a ghost haunting physics. Then, in 1905, a young patent clerk in Switzerland named Albert Einstein proposed something radical. Einstein wasn't trying to save the ether. He wasn't trying to explain away the Michelson-Morley result with complicated hypotheses about contracting rulers and slowing clocks. Instead, he did something bolder. He embraced the result. He made it a fundamental principle of nature. Light travels at the same speed for all observers, regardless of their motion. Period. No exceptions, no special reference frame, no ether, just a universal constant that everyone measures the same way. What distinguished Einstein from Lorentz and Poincaré wasn't the mathematics. The equations they developed were essentially the same. What distinguished Einstein was the interpretation. Lorentz saw length, contraction, and time dilation as real physical effects caused by motion through the ether. Einstein saw them as consequences of a deeper truth about the nature of space and time themselves. There was no ether. There was no absolute rest. There was only the invariant speed of light and the relativity of everything else. Einstein combined his light postulate with another principle. The laws of physics are the same for all observers in uniform motion. If you're in a windowless room moving at constant velocity, no experiment you perform inside that room can tell you whether you're moving or standing still. All motion is relative. There's no absolute rest. These two principles, together, had consequences that seemed impossible. They implied that space and time couldn't be the separate, independent quantities we always assumed. They implied that the very foundations of physics needed to be rebuilt from the ground up. Think about what it means for light to travel at the same speed for everyone. Imagine you're standing still and I'm flying past you at half the speed of light. That's 150,000 kilometers per second. We both measure the speed of a beam of light traveling in the same direction I'm moving. According to everyday intuition, I should measure the light moving slower relative to me. I'm already moving fast in the same direction as the light. The light should only be pulling ahead of me at half the speed of light. That's how velocities add. That's how everything else works. But Einstein said no. We both measure exactly 300,000 kilometers per second. You, standing still, measure the light at 300,000. Me, flying at half light speed, also measure the light at 300,000, not 150,000. The full 300,000. How can this possibly be? There's only one way. If we can't agree on the speed of light, and speed is distance divided by time, then we must disagree about distance and time themselves. Your measurement of distance must be different from my measurement. Your measurement of time must be different from mine. The only way light can travel at the same speed for both of us is if space and time themselves are flexible. If they change depending on how you're moving. This is where the fabric starts to reveal itself. Space and time aren't separate things that we measure independently with rulers and clocks that always agree. They're connected. They're intertwined. What you measure as space depends on your motion. What you measure as time depends on your motion. And when one changes, the other compensates. They trade off against each other in precisely the right way to keep the speed of light constant for everyone. Let me give you a concrete example to make this real. Imagine a spaceship flying past Earth at 90% of the speed of light. That's 270,000 kilometers per second. An incredible velocity that nothing we've ever built comes close to achieving. On the spaceship, there's a special kind of clock. This clock works by bouncing a light beam between two mirrors. One mirror at the floor, one at the ceiling. Every time the light completes a round trip, the clock ticks once. From the spaceship's perspective, everything is normal. The light bounces straight up and down, up to the ceiling mirror, back down to the floor mirror. The distance it travels is just twice the distance between the mirrors. If the mirrors are 1 meter apart, the light travels 2 meters per tick. Simple, straightforward. But now consider what this looks like from Earth's perspective. The spaceship is moving. While the light travels up toward the ceiling, the spaceship moves forward. So the light has to travel diagonally to catch up with the moving mirror. While the light travels back down, the spaceship moves forward again. Another diagonal path. From Earth's perspective, the light zigzags through space, covering more distance than the simple up and down path seen on the spaceship. And here's the crucial point. Light always travels at the same speed, 300,000 kilometers per second. No exceptions, not even for this light beam inside the spaceship. From Earth's perspective, the light has to travel more distance, but it can't travel faster to compensate, so it must take more time. The clock on the spaceship, as seen from Earth, runs slower. Each tick takes longer. Time itself is passing more slowly on the moving spaceship, at least from Earth's perspective. This is called time dilation. And it's not an illusion. It's not a trick of perception or a problem with the clocks. It's real. The passage of time itself is different for different observers depending on their relative motion. A clock moving past you runs slow compared to your clock. And this isn't because something is wrong with the moving clock. It's because time itself flows differently depending on how you're moving. And it's not just time. Space gets affected too. From Earth's perspective, the spaceship appears shorter than it would if it were stationary. This is called length contraction. The spaceship is compressed to about 44% of its rest length. If it's 100 meters long when parked, it's only about 44 meters long when flying past at 90% of light speed. The spaceship isn't crushed by some force. It's not damaged. The astronauts inside don't notice anything strange. From their perspective, the spaceship is perfectly normal. It's Earth and everything on it that appears compressed. The contraction is mutual. Each observer sees the other as contracted. Each observer measures the other's clocks as running slow. Now here's the crucial insight. These effects, time dilation and length contraction, aren't separate phenomena that just happen to occur together. They're two aspects of a single, deeper truth. Space and time aren't independent. They're woven together into a single fabric. And different observers, moving at different speeds, slice this fabric differently. What one observer calls space, another observer calls a mixture of space and time. What one observer calls time, another observer calls a mixture of time and space. This unified fabric is what we call space-time. And understanding it requires letting go of our everyday intuitions about space and time as separate things. It requires accepting that the division between where and when is not fundamental. It's an artifact of our particular state of motion. The mathematical framework for space-time was developed shortly after Einstein's 1905 paper by his former mathematics professor, Hermann Minkowski. In 1908, Minkowski gave a famous lecture where he said something profound. He said, "Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." What Minkowski realized was that while different observers disagree about distances in space and durations in time, there's something they all agree on. There's an invariant quantity, a measurement that comes out the same no matter how you're moving. This quantity is called the space-time interval. Suppose two events happen. Event A, a firecracker goes off here and now. Event B, another firecracker goes off over there and later. Different observers will measure different spatial distances between the events. They'll also measure different time intervals between them. An observer moving to the right might measure a smaller spatial distance and a larger time interval. An observer moving to the left might measure the opposite. Everyone disagrees. But if you combine the spatial distance and the time interval in a specific way, using what's called the Minkowski metric, you get a number that everyone agrees on. The mathematical details don't matter for understanding the concept. What matters is this: the result is invariant. All observers, no matter how they're moving, calculate the same value for the spacetime interval between any two events. This invariant interval is what makes spacetime real. It's telling us that there's a genuine, objective structure underlying our separate perceptions of space and time. Different observers are just seeing different cross-sections of the same underlying four-dimensional reality. They disagree about space, they disagree about time, but they agree about space-time. Think of it like this. Imagine a loaf of bread. You can slice it straight across, perpendicular to the length of the loaf, or you can slice it at an angle. Each slice looks different. The shape changes. The pattern of the crust changes. A straight slice might be circular, an angled slice might be elliptical, but every slice comes from the same loaf. The loaf itself doesn't change just because you slice it differently. Space-time is the loaf. Space and time separately are the slices. Different observers, moving at different speeds, are slicing space-time at different angles. They get different amounts of space in their slice. They get different amounts of time. Their slices have different shapes, but the underlying four-dimensional structure, the space-time loaf itself, remains the same. This has profound implications. It means that space and time don't have independent existence. Only space-time does. When you measure a distance with a ruler, you're not measuring something fundamental. You're measuring a projection, a shadow of the true four-dimensional reality onto your particular slice. When you measure a duration of time with a clock, same thing. A projection, a shadow, not the underlying reality, but an appearance that depends on your state of motion. The true reality is the four-dimensional continuum where all events have positions, not positions in space, not positions in time, positions in space-time, four coordinates, three spatial and one temporal, inseparably linked into a single four-dimensional location. This is called the relativity of simultaneity, and it's perhaps the strangest consequence of space-time. There is no universal now, no cosmic clock ticking away that everyone agrees on. What counts as the present moment depends on how you're moving. Events that you consider simultaneous, happening at the same time but different places. Another observer might consider sequential, happening at different times. This doesn't mean anything goes. Not every ordering is possible. If one event causes another, if information or influence travels from the first event to the second, then the ordering is fixed. Everyone will agree that the cause came before the effect. The structure of space-time preserves causality. You can't change the order of cause and effect by moving fast enough. But for events that don't causally influence each other, events that are too far apart in space for light to travel between them in the time available, the ordering is genuinely relative. It depends on the observer. We'll explore the deep implications of this causal structure in Part 3, including why nothing can travel faster than light and what would happen if it could. Your intuitions about space and time as separate things come from the fact that you move slowly. Compared to light, you're practically stationary. The fastest human beings have ever traveled was the Apollo astronauts returning from the moon at about 11 kilometers per second. That's fast by human standards, but it's only about 0.004% of the speed of light. Essentially zero. At the speeds you experience in daily life, the differences between your space-time slice and another person's are incredibly tiny, much too small to notice, much too small to measure with ordinary instruments. So space seems like space, and time seems like time, and they seem completely separate. A meter is a meter, a second is a second. Your ruler and clock agree with everyone else's. But they're not separate. They never were. The separation was always an illusion created by our slow-motion existence. We evolved to understand the world at human speeds, and at human speeds, the unity of space-time is hidden. But when you look deeper, when you look at nature at its most fundamental level, when you study particles moving near light speed, or light itself crossing vast distances, you find space-time, a single unified structure where space and time are intertwined, where measurements depend on motion, where the only invariant is the space-time interval itself. And we're just getting started, because this flat, uniform space-time of special relativity is just the beginning. Special relativity describes space-time in the absence of gravity. It describes how space and time behave when no massive objects are curving the fabric. But our universe has mass, it has energy, and wherever there's mass or energy, something remarkable happens. Space-time curves, it bends, it warps, and this curvature is what we experience as gravity. Now we understand that space and time are unified into space-time. But so far, we've been talking about flat space-time, the space-time of special relativity, a space-time where nothing particularly interesting is happening gravitationally, no massive objects nearby, no strong gravitational fields, just empty space, flat and featureless, stretching out in all directions like an infinite, perfectly smooth sheet. But that's not the universe we live in. Our universe has mass, it has energy, it has stars burning with the fury of nuclear fusion, it has planets spinning through the void, it has galaxies containing hundreds of billions of stars, and clusters of galaxies containing thousands of galaxies, and superclusters stretching across hundreds of millions of light years. It has black holes where matter has collapsed so completely that nothing can escape. It has neutron stars where a mass greater than the sun is compressed into a sphere the size of a city. And wherever there's mass or energy, something remarkable happens. Space-time curves. This is Einstein's general theory of relativity, published in 1915, 10 years after his special theory. And it's one of the most beautiful and profound ideas in all of physics. Perhaps in all of human thought. It takes the concept of space-time from special relativity and extends it in a way that seemed almost magical at the time. It says space-time isn't just a passive stage on which events happen. It's a dynamic player. It responds to the matter and energy within it. It bends, it flexes, it warps, and in doing so, it tells matter how to move. Let me take you through the reasoning that led Einstein to this extraordinary idea, because it didn't come from nowhere. It wasn't a random flash of genius. It came from Einstein thinking deeply, persistently, obsessively about what gravity actually is, about what it means for objects to attract each other across empty space. Consider the puzzle that Isaac Newton solved in the 1600s. Objects fall, drop something, and it accelerates toward the ground. The moon orbits Earth, circling us once every 27 days. Earth orbits the sun, completing one loop every year. Comets sweep in from the outer solar system on long elliptical paths. Newton unified all of this with his law of universal gravitation. Every object with mass attracts every other object with mass. The force depends on the masses involved and the distance between them. Double the distance, the force drops to 1/4. Triple the distance, 1/9. This single mathematical law explained falling apples and orbiting planets. It predicted the paths of comets. It unified heaven and earth under one principle. Newton's theory of gravity was spectacularly successful. For over 2 centuries, it reigned supreme. It predicted the existence of Neptune before anyone had seen it, just from perturbations in the orbit of Uranus. It sent spacecraft to the moon and to Mars. It seemed like the final word on gravity. But Newton's theory had a problem. A deep, philosophical problem that Newton himself recognized and admitted he couldn't solve. His theory said that masses somehow reach across empty space to pull on each other. But how? Through what mechanism? What actually carries the gravitational influence from one object to another? If the sun disappeared right now, according to Newton's theory, Earth would instantly fly off in a straight line. The gravitational influence would vanish immediately. Not at the speed of light, not at any finite speed. Instantly, as if the sun's gravity was somehow present everywhere at once, and its disappearance would be felt everywhere at once. Newton called this action at a distance, and it troubled him deeply. In a letter to a colleague, he wrote that the idea of one body acting on another through a vacuum without any intermediary was so absurd that no person with any competence in philosophical matters could accept it. And yet his theory required exactly this absurdity. It worked, it predicted, but it couldn't explain. Einstein was deeply bothered by this too, but for a more specific reason. After developing special relativity, he knew that nothing could travel faster than light. Information, influence, causality, all limited by the speed of light. This was woven into the geometry of space-time itself, but Newtonian gravity seemed to violate this. If the sun vanished, how could Earth know instantly? Wouldn't the information have to travel somehow? Wouldn't it be limited by the speed of light? Einstein spent years thinking about this problem. From 1907 to 1915, 8 years of intense effort, false starts, mathematical struggles, and conceptual breakthroughs. And he had a crucial insight that came from a simple observation about falling objects. Imagine you're in an elevator, a normal elevator in a tall building. You're standing there, feeling your weight, when suddenly the cable snaps. The elevator plunges downward. You're in free fall. What do you experience? You float. You feel weightless. If you let go of an apple, it doesn't fall to the floor. It floats next to you. If you pour water from a glass, it hangs in the air in a shimmering sphere. Everything in the elevator falls together at exactly the same rate. So relative to the elevator, nothing falls at all. You're weightless. This observation goes back to Galileo in the 1600s. All objects fall at the same rate regardless of their mass. A feather and a hammer, dropped in a vacuum where air resistance doesn't interfere, hit the ground at exactly the same time. Apollo 15 astronaut David Scott demonstrated this on the moon in 1971, dropping a falcon feather and a hammer. They fell side by side and landed together. Galileo was right. This is deeply strange if you think about it. Why should gravity accelerate all objects equally? Heavier objects have more gravitational force pulling them down, but they also have more inertia, more resistance to acceleration. And these two effects, the extra force and the extra inertia, cancel out exactly, perfectly, to as many decimal places as we've ever measured. This seems like an incredible coincidence. Why should gravitational mass, which determines how strongly you're pulled by gravity, be exactly equal to inertial mass, which determines how hard you are to accelerate? Einstein realized this equivalence, this fact that everything falls the same way, was telling us something profound about the nature of gravity itself. He called it the equivalence principle, and he took it seriously as a fundamental truth about nature. Not a coincidence to be explained, but a clue to be followed. Here's the equivalence principle in action. Imagine you're in a sealed room with no windows. You feel weight. Your feet press against the floor. Objects fall when you drop them. You feel completely normal. But here's the question. Can you tell whether you're standing on Earth, experiencing gravity, or whether you're in a rocket ship far from any planet, accelerating through space at 9.8 meters per second squared? Einstein's answer: no, you cannot tell the difference. The experiences are physically indistinguishable. Gravity pulling you down and acceleration pushing the floor up into you produce exactly the same effects. Drop an apple and it falls, either because gravity pulls it or because the floor accelerates up to meet it. You can't tell which. This seems like a strange coincidence. Why should a gravitational field and an accelerating reference frame be indistinguishable? Unless they're not actually different things. Unless what we call gravity is actually a kind of apparent force, like the force you feel pressing you into your seat when a car accelerates. Unless objects in a gravitational field aren't really being pulled at all, but are instead in a state of natural motion through something. That something is space-time. Here's Einstein's revolutionary insight, the insight that changed physics forever. Objects in free fall aren't being pulled by gravity. They're not experiencing any force at all. They're simply moving in a straight line through space-time, the straightest possible line, what mathematicians call a geodesic. But here's the key. Space-time near massive objects is curved. It's not flat like the space-time of special relativity. It's warped and bent by the presence of mass and energy. And when you draw a straight line through curved space, that straight line looks curved to someone who thinks space is flat. Think about an airplane flying from New York to London. If you look at the flight path on a flat map, the shortest route looks curved. It bulges up toward the North Pole, passing over Canada and Greenland, rather than taking what looks like a straight shot across the Atlantic. This seems wrong. Why doesn't the plane just fly straight? But the plane is flying straight. It's following a geodesic, the shortest path between 2 points on the curved surface of Earth. On a globe, you can see it clearly. Stretch a string between New York and London on a globe, and it follows that northern route. It's the flat map that distorts reality, making the straight path look curved. The airplane isn't being pulled northward by some mysterious force. It's just following the straightest path through curved space. The curvature of Earth's surface makes the shortest path look curved on a flat representation. Gravity works the same way. Space-time near Earth is curved by Earth's mass. Objects in free fall, objects with no forces acting on them, follow the straightest paths through this curved space-time. They follow geodesics. We see them accelerating toward Earth, curving toward the ground, and we interpret this as gravity pulling them. We imagine an invisible force reaching out from Earth, grabbing the apple, tugging it downward. But from the perspective of space-time geometry, there's no force at all. The apple is moving in a straight line through space-time. It's not being pulled, it's not being pushed. It's simply following the natural geometry of the curved space-time it finds itself in. The geodesic happens to lead toward Earth because that's how Earth's mass has curved the space-time around it. This is what Einstein meant when he said gravity isn't a force, it's geometry. The curvature of space-time tells objects how to move, and matter tells space-time how to curve. This last part is crucial. What causes space-time to curve in the first place? Mass and energy. The sun curves the space-time around it, creating the geometry that guides the planets in their orbits. Earth curves the space-time around it, creating the geometry that makes apples fall and satellites orbit. You curve the space-time around you, though by an incredibly tiny amount because your mass is so small compared to planets and stars. The more mass or energy in a region, the more space-time curves. The sun, with its enormous mass, creates significant curvature extending throughout the solar system. A neutron star, with a mass greater than the sun packed into a city-sized sphere, creates extreme curvature. A black hole, where mass has collapsed beyond a critical point, creates curvature so severe that nothing can escape. Einstein expressed this relationship between matter and curvature in his field equations. These equations are the heart of general relativity, the mathematical core of the theory. On one side of the equations, you have terms describing the curvature of space-time, how it bends and warps at every point. On the other side, you have terms describing the distribution of mass and energy, how much is present and how it's moving. The equations relate them. They tell you how a given distribution of mass and energy curves space-time. And they tell you how objects move through that curved space-time. The physicist John Wheeler summarized it beautifully. Space-time tells matter how to move. Matter tells space-time how to curve. This reciprocal relationship is what makes general relativity so different from Newton's gravity. In Newton's picture, space is a passive stage. Masses exert forces on each other across that stage. In Einstein's picture, space-time is an active participant. It responds to mass. It curves. And that curvature guides motion. Let me give you some examples of what curved space-time actually does, because the theory isn't just abstract mathematics. It has concrete, measurable, practical consequences. Consider Earth orbiting the Sun. In Newton's picture, the Sun pulls Earth toward it with gravitational force. This force points from Earth toward the Sun. But Earth is also moving tangentially, perpendicular to this force. The combination of the inward pull and the tangential motion creates an orbit. Earth keeps falling toward the Sun but keeps missing because it's also moving sideways. It's a balance of forces creating an elliptical path. In Einstein's picture, the story is completely different. The Sun curves the space-time around it. Earth moves through this curved space-time, following a geodesic. From Earth's perspective, it's moving in a straight line through space-time. There's no force acting on it. It feels no pull. It's simply coasting along the straightest available path. But to someone watching from far away, someone who imagines space-time as flat, Earth appears to be circling the Sun. Its straight line through curved space-time looks like an ellipse to someone who doesn't account for the curvature. The orbit itself is what a straight line looks like in the curved geometry created by the Sun's mass. This might seem like a distinction without a difference. Newton says the Sun pulls Earth. Einstein says Earth follows a geodesic through curved space-time. Either way, Earth orbits. Why does it matter which description is correct? It matters because the descriptions make different predictions. Newton's theory predicts that orbits should be perfect ellipses, returning to exactly the same point after each lap. Einstein's theory predicts that orbits should precess, rotating slowly over time. The point of closest approach to the Sun should shift gradually with each orbit. This precession is tiny for Earth. But for Mercury, the innermost planet, orbiting close to the Sun where space-time curvature is strongest, the effect is measurable. Mercury's orbit precesses by a small amount that Newton's theory couldn't explain. Astronomers had known about this discrepancy since the 1800s. They even proposed a hidden planet closer to the Sun to account for it. Einstein's theory explained the discrepancy exactly. The extra precession comes from the curvature of space-time near the Sun. When Einstein calculated Mercury's precession using general relativity, he got exactly the right answer. This was one of the first confirmations that his theory was correct. Now consider time. We talked about time dilation in special relativity, where moving clocks run slow compared to stationary ones. General relativity adds another kind of time dilation: gravitational time dilation. Clocks in stronger gravitational fields, deeper in the curvature of space-time, run slower than clocks in weaker fields. This isn't a mechanical effect on the clocks. It's not that gravity somehow interferes with clock mechanisms. It's that time itself passes more slowly in regions of stronger curvature. A second near a massive object is genuinely shorter than a second far from that object. Not shorter in appearance, shorter in reality. This has been measured directly, many times, with extraordinary precision. GPS satellites provide the most familiar example. These satellites orbit Earth at an altitude of about 20,000 kilometers, where gravity is weaker than at Earth's surface. The gravitational effect makes the satellite clocks run faster by about 45 microseconds per day. But the satellites are also moving at high speed in their orbits, which causes a special relativistic slowing of about 7 microseconds per day. The net effect is that satellite clocks run faster by about 38 microseconds per day compared to clocks on the ground. That might sound tiny. 38 microseconds. Who cares about 38 millionths of a second? But GPS works by measuring the time it takes radio signals to travel from satellites to your phone. Light travels about 300 meters in 1 microsecond. 38 microseconds of error translates to about 11 kilometers of position error per day. Your GPS would tell you you're in the wrong city. GPS systems correct for both of these relativistic effects. They adjust the satellite clocks to account for general and special relativistic time dilation. Every time you use GPS navigation, every time you check your location on your phone, you're relying on Einstein's theories being correct. The technology works only because space-time curves around Earth, exactly as general relativity predicts. Here's another example. Light bends around massive objects. This effect is called gravitational lensing. When light from a distant star passes near a massive object like the Sun, the light follows a geodesic through the curved space-time, and that geodesic bends toward the Sun. The light curves. So, the star appears to be in a slightly different position than it actually is. Newton's theory also predicts some bending of light, treating light as particles affected by gravity, but Einstein's theory predicts exactly twice as much bending. The difference comes from the curvature of space itself, which Newton's theory doesn't include. This effect was first measured during a total solar eclipse in 1919. British astronomer Arthur Eddington organized expeditions to 2 locations where the eclipse would be visible. During totality, when the moon blocked the sun's glare, astronomers photographed stars appearing near the sun. They compared these positions to where the same stars appeared at night, when the sun wasn't nearby. The stars near the sun appeared shifted, displaced from their normal positions by a tiny amount. And that amount matched Einstein's prediction, not Newton's. The announcement of these results made headlines around the world. Einstein became famous overnight. The curved space-time theory, which had seemed like abstract mathematics, was confirmed by observation. Light really does bend around massive objects. Today, gravitational lensing is a powerful tool in astronomy. When light from a distant galaxy passes near a closer galaxy or galaxy cluster, the curvature bends the light. The distant galaxy appears distorted, sometimes stretched into arcs, sometimes multiplied into multiple images. By analyzing these distortions, astronomers can map the distribution of mass in the universe, including dark matter that we can't see directly. Let me describe space-time curvature more carefully because it's often misunderstood. The most common visualization shows a rubber sheet stretched flat, with a heavy ball sitting on it, creating a depression. Smaller balls, rolling across the sheet curve toward the depression, illustrating how gravity works. This picture is helpful as a starting point, but also misleading in important ways. It shows only 2 spatial dimensions, while real spacetime has 3 space dimensions plus time. It suggests that gravity is caused by the depression pulling things down toward the heavy ball, but that's actually using gravity, the pull toward Earth holding the sheet in place, to explain gravity. It's circular. Most importantly, the rubber sheet picture doesn't capture the time component of space-time curvature at all. And this is where the real physics lies. In reality, space-time curvature involves both space and time. Near a massive object like Earth, space is slightly curved. If you could measure with enough precision, you'd find that rulers aren't quite straight, that triangles don't quite have angles that add up to 180 degrees, that the geometry departs slightly from the flat Euclidean geometry you learned in school. But more importantly, time is curved too. Time passes at different rates at different locations relative to the massive object. Closer to the mass, time runs slower. Farther away, time runs faster. This temporal curvature is actually the dominant effect for most everyday situations involving gravity. The reason you fall toward Earth isn't primarily because space is curved. It's because time is curved. Let me try to explain this more intuitively, because it's a subtle point that most explanations skip over. Remember that everything moves through space-time. Even when you're standing perfectly still spatially, not moving left or right or up or down, you're still moving through time. Time passes. You age. Events happen in sequence. You're always traveling through space-time, and when you're spatially stationary, all of that motion is through the time dimension. Now, near a massive object like Earth, time runs slower. If you're standing on Earth, time at your head runs slightly faster than time at your feet, because your head is slightly farther from Earth's center, slightly higher in the gravitational field. The difference is tiny, about 1 part in 10 to the 16th power for a person standing on Earth, completely unmeasurable in daily life. But it's real. Here's where it gets interesting. Because you're always moving through time, and because time runs at different rates at different heights, this creates an effective acceleration toward the region where time runs slowest. Your head is trying to move through time faster than your feet, but you're a rigid object. You can't let your head outpace your feet, so your whole body accelerates toward Earth, toward the region where time is slowest. You're not being pulled by a force. You're following the geometry of space-time. And that geometry, with time running at different rates at different locations, naturally directs motion toward massive objects. This is why gravity is so fundamentally different from other forces. Electromagnetic forces push on charged particles, accelerating them in particular directions depending on their charge. The strong nuclear force holds atomic nuclei together. These are forces in the traditional sense. They accelerate specific particles in specific ways depending on the particle's properties. But gravity doesn't push or pull. It curves space-time, and everything moves through that curved space-time according to the same rules. That's why everything falls at the same rate. The motion isn't determined by what the object is, what it's made of, how much charge it has. It's determined by the geometry of space-time itself. Everything follows geodesics, and the geodesics near Earth lead toward Earth. Einstein's field equations have been tested in countless ways over the past century. The precession of Mercury's orbit, gravitational time dilation, gravitational lensing, the Shapiro delay, where light passing near the sun takes slightly longer than expected because it's traveling through curved space-time, frame dragging, where a rotating mass drags space-time around with it. Every test confirms general relativity's predictions with stunning accuracy. Gravitational waves deserve special mention. General relativity predicts that when massive objects accelerate, they create ripples in space-time itself, waves of curvature that propagate outward at the speed of light. Just as shaking a charged particle creates electromagnetic waves, accelerating a massive object creates gravitational waves. In 2015, the LIGO detector finally measured gravitational waves directly. They came from 2 black holes spiraling into each other and merging about 1.3 billion light-years away. Each black hole had a mass of roughly 30 times the Sun. As they spiraled closer and closer, moving faster and faster, they radiated gravitational waves that carried away energy. In the final fraction of a second, they merged into a single black hole. The collision was so violent that it converted about 3 solar masses of matter into pure gravitational wave energy. Yet by the time these waves reached Earth, after traveling for 1.3 billion years, they stretched and compressed the 4-kilometer detector arms by less than 1/10,000th the width of a proton. And we detected them. We measured this tiny change in space-time. We felt the universe ring. General relativity also predicts objects so dense that space-time curves catastrophically. These are black holes. When enough mass is compressed into a small enough region, the curvature becomes so extreme that something qualitative changes. Escape becomes impossible. Not because of overwhelming gravitational force, but because the geometry of space-time itself points inward. All paths lead to the center. There are no paths leading out. The boundary where this happens is called the event horizon. It's not a physical surface. There's nothing material there. No wall, no barrier, no membrane you could touch. It's a boundary in space-time, a threshold in the geometry. Cross it, and every possible path through space-time leads further into the black hole. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow. This wasn't a traditional photograph. The Event Horizon Telescope is a network of radio telescopes around the world, working together as a single Earth-sized instrument. They observed the black hole at the center of the galaxy M87, about 55 million light-years away. This black hole has a mass of about 6.5 billion times the mass of our Sun. The image showed a bright ring of light surrounding a dark shadow. The ring is light from hot gas orbiting the black hole, bent around the black hole by extreme space-time curvature. Some of this light orbits the black hole multiple times before escaping toward us. The shadow is the event horizon itself, the region from which no light can escape. For the first time, we saw the boundary of a black hole. Space-time curvature is real. It shapes the paths of planets and light beams and gravitational waves. It slows time near massive objects. It creates black holes and gravitational lenses and the orbital mechanics of everything from moons to galaxy clusters. It's not a metaphor or an approximation or a mathematical convenience. It's the actual structure of reality. And this leads us to a crucial point. Space-time isn't just a background, a stage on which physics happens. It's an active participant. It responds to matter and energy. It tells matter how to move. Matter tells it how to curve. They're engaged in a constant dynamic interplay that shapes everything we see. Understanding space-time curvature changes how you see the cosmos. The apple doesn't fall because Earth reaches out and pulls it down with some mysterious force. The apple falls because space-time is curved, and falling is what straight-line motion looks like in curved space-time. The moon doesn't orbit because Earth tugs on it with gravitational attraction. The moon orbits because that's what a geodesic looks like near a massive body. Every orbit, every falling object, every gravitational phenomenon becomes geometry. And once you see it this way, you can't unsee it. Gravity becomes geometric. Motion becomes geodesic. Force becomes an illusion created by our assumption that space-time is flat. And space-time becomes the very substance of physical reality, curving and flexing and waving in response to the matter and energy within it. We've learned that space-time is the unified fabric of existence. We've seen how mass and energy curve this fabric, creating what we experience as gravity. Now we need to explore something even more fundamental. We need to understand what space-time permits and what it forbids. Because space-time isn't just a passive stage on which events unfold. It has rules, deep, structural rules that constrain what can happen in the universe. Rules about causality itself, about cause and effect, about what can influence what. These rules aren't arbitrary. They aren't laws imposed from outside by some cosmic legislator. They emerge from the very geometry of space-time. They're woven into the fabric of reality at the most fundamental level. And understanding them is essential to understanding why the universe works the way it does. Let's start with a concept that's central to understanding space-time structure: the light cone. Imagine an event. Something happens at a specific place and time. A firecracker explodes. A clock strikes midnight. You snap your fingers. A star goes supernova. Whatever it is, this event has a position in space-time, 4 coordinates, 3 spatial coordinates telling you where it happened, 1 temporal coordinate telling you when, a single point in the 4-dimensional continuum we've been discussing. Now ask a question that seems simple but has profound implications. What other events can this event influence? If the firecracker explodes, what parts of space-time can feel the effects of that explosion? What other events could have been affected by it? The answer depends entirely on the speed of light. Nothing travels faster than light. Not matter, not energy, not information, not any form of influence whatsoever. This is a fundamental constraint woven into spacetime's geometry. It's not an engineering limitation that we might someday overcome with better technology. It emerges from the structure of reality itself. So, if our event is a firecracker exploding at a specific location and time, the influence of that explosion spreads outward at the speed of light at most. Light itself, of course, travels at exactly the speed of light. Sound travels much slower, about 340 meters per second in air. Physical debris from the explosion travels slower still. But nothing, absolutely nothing, travels faster than light. This means there's a boundary, a sharp dividing line in space-time between what the explosion can affect and what it cannot. The explosion happens at time zero at a specific location. After 1 second, its influence could have reached points up to 300,000 kilometers away in any direction. That's 1 light second. After 2 seconds, the boundary of possible influence has expanded to 2 light seconds, 600,000 kilometers. After 1 year, 1 light year, the boundary keeps expanding at the speed of light, forever. When you draw this expanding boundary in space-time, with time as one axis and space as the other axis, it forms a cone shape. This is the future light cone of the event. The cone opens upward into the future, expanding as time passes. Every event that could possibly be influenced by the firecracker explosion lies inside or on this cone. Events inside the cone are close enough and late enough that something from the explosion could have reached them. Events on the cone itself are exactly at the boundary, reachable only by light traveling at maximum speed. Events outside the cone are beyond the explosion's influence. They're too far away. Even light, traveling at the maximum possible speed, couldn't have reached them yet. The explosion simply cannot affect them. No matter how much energy the explosion released, no matter what mechanisms might be involved, those events are causally disconnected from the explosion. They're beyond its reach. Similarly, there's a past light cone. This points backward in time, opening downward into the past. It contains all events that could have influenced the firecracker explosion. Everything that could have sent light, or anything slower, to the location of the firecracker before it went off. These are events that might have caused the explosion, or contributed to it, or affected it in some way. Together, the past and future light cones divide all of space-time into distinct regions relative to any event. Inside the future light cone are events that the original event can potentially influence. These events are in the absolute future of the original event. And here's something crucial. Everyone agrees about this. Every observer, regardless of how they're moving, regardless of their reference frame, agrees that these events happen after the original event. The ordering is fixed, absolute, invariant. Inside the past light cone are events that could have influenced the original event. These are in the absolute past. Again, everyone agrees. These events happened before. The ordering is fixed. But outside both cones lies a vast region of space-time. Events in this region are what physicists call space-like, separated from the original event. They're too far away in space, and too close in time for any causal connection. Light couldn't travel between them. Nothing could. These events cannot influence the original event, and the original event cannot influence them. They're causally disconnected. And here's the strange part. For these space-like separated events, the notion of before and after becomes relative. Some observers, moving in certain ways, will say these events happened before the original event. Other observers, moving differently, will say they happened after. There's no absolute fact of the matter. The ordering depends on your reference frame. It depends on how you're moving. Light cones define the causal structure of space-time. They separate what can affect what from what cannot. They impose order on events that have causal relationships and leave the ordering ambiguous for events that don't. This is the architecture of causality, the blueprint that determines which events can influence which other events, and in what order. This causal structure is precisely why nothing can travel faster than light. Suppose you could send a signal faster than light. Think about what would happen. You send the signal at time 0 from your location. Because the signal travels faster than light, it leaves your future light cone. It reaches events that are outside your light cone. Events that are space-like, separated from your sending of the signal. Now remember what we said about space-like separated events. Different observers disagree about their ordering. Some observers would say those events happen after you send the signal, but other observers, moving in certain directions, would say those events happen before you send the signal. From their perspective, the signal arrives before it was sent. The effect precedes the cause. This might seem like just a curiosity of perspective. Who cares what some hypothetical moving observer thinks? But here's where it gets serious. Imagine you send a faster-than-light message to a friend in a distant galaxy. Your friend receives it and immediately sends a faster-than-light reply back to you. From your perspective, you sent a message and received a reply. Normal enough. But because of how reference frames work in special relativity, if both signals travel faster than light, you could arrange things so that you receive the reply before you sent the original message. Not just from some observer's perspective, from your own perspective. In your own reference frame, you'd read the reply, learn its contents, and then later send the original message that prompted it. This creates paradoxes. What if the reply says something that causes you to decide not to send the original message? Then the reply would never be sent, which means you'd never receive it, which means you'd send the original message after all, which means you'd receive the reply, which means you wouldn't send the message. And round in logical circles. This isn't science fiction speculation. This is mathematics. The equations of special relativity make it absolutely clear. Faster than light travel or communication, within the framework of space-time as we understand it, would violate causality. It would allow effects to precede their causes. It would break the logical structure of reality. It would permit paradoxes that have no resolution. So, space-time forbids it, not as a rule imposed from outside, but as a structural feature of reality itself. The speed of light is the boundary of causality. The edge of the light cone is the edge of what can influence what. Cross that boundary, and logic breaks down. Causality fails. The coherent flow from cause to effect dissolves into contradiction. Let me put this differently, because it's such an important point. You might think of the speed of light as just how fast light happens to go, a property of electromagnetic radiation, the result of some particular physics of photons. But that's not the right way to think about it. The speed of light is the speed of causality. It's the rate at which cause and effect propagate through space-time. It's the maximum speed at which any influence, any information, any causal connection can travel. Light travels at this speed because light is massless, and massless things always travel at the speed of causality. But even if light didn't exist, even if photons weren't part of our universe, there would still be this maximum speed, this cosmic speed limit, this boundary to how fast causality can propagate. Particles with mass can never reach this speed. As they accelerate, approaching light speed, something strange happens. They require more and more energy for each additional increment of velocity. Not a constant amount more, exponentially more. The energy required approaches infinity as the speed approaches light speed. You can never quite get there. You can get arbitrarily close, 99%, 99.9%, 99.999%, but never 100%. The final gap can never be closed. This isn't just theoretical prediction, it's measured constantly at particle accelerators around the world. Protons at the Large Hadron Collider are accelerated to approximately 99.99999% of light speed, incredibly close to the limit, but not quite there. And those final tiny fractions would require more energy than exists in the entire visible universe. At these extreme velocities, relativistic effects become enormous. The proton's internal processes slow down by factors of thousands. From the proton's perspective, the entire 27-kilometer ring is length contracted to just a few meters. These effects aren't quirks of the mathematics, they're real. They're built into the design of the accelerators. The machines wouldn't work if special relativity were wrong. Let's explore what light cones reveal about black holes. Building on what we learned in part 2, we discussed how black holes form when enough mass collapses into a small enough region that space-time curves catastrophically. The event horizon is the boundary beyond which escape becomes impossible. But now we can understand this more deeply in terms of causal structure. Near a black hole, something remarkable happens to light cones. As you approach the event horizon, your future light cone begins to tilt. Far from a black hole, your light cone looks normal. The future cone opens upward and outward. You can travel in any direction. You can escape to infinity if you want. Your future contains all sorts of possibilities. But as you get closer to the event horizon, space-time curvature begins to warp your light cone. It leans toward the black hole. Paths that would have led outward now lead inward. Paths that would have led inward lead even more inward. Your options narrow. At the event horizon, the tilting becomes complete. Your entire future light cone points toward the singularity at the center of the black hole. There is no path, not even a path at the speed of light, that leads outward. The outward direction is no longer part of your future. It's become space-like. Reaching the region outside the horizon would require traveling faster than light, which space-time forbids. This is what makes a black hole truly black. Not the strength of gravity, though that's certainly extreme, but the warping of causal structure, the tilting of light cones until escape becomes geometrically impossible. The singularity isn't pulling you in with some irresistible force. The singularity is simply the only direction your future can go. It's where all your possible paths converge. All your geodesics lead there. This understanding of black holes in terms of light cones resolves a common confusion. People sometimes ask why light can't escape a black hole. Light is the fastest thing in the universe, they reason. If anything could escape, light should. But this misunderstands the situation. It's not that light tries to escape and fails, it's that there's no outward direction for light to travel. The geometry of space-time inside the event horizon contains no paths that lead out. All geodesics point inward. Light follows geodesics just like everything else, and all the geodesics lead to the singularity. The cosmic horizon presents another fascinating application of light cones. The observable universe has a boundary, but it's not a physical wall. It's a causal boundary determined by light cones and the age of the universe. The universe is about 13.8 billion years old. Light from events that happened shortly after the Big Bang has been traveling toward us for almost that entire time. The farthest we can possibly see is determined by how far light could have traveled in the age of the universe. This defines the edge of the observable universe, our cosmic horizon. But here's where it gets interesting. Because the universe has been expanding, that cosmic horizon isn't simply 13.8 billion light years away. The expansion of space has stretched the distance. The edge of the observable universe is now about 46 billion light years away in every direction. Light that has been traveling toward us since the early universe has been chasing us through expanding space, and we've been receding from its origin point the whole time. Beyond this horizon, there's almost certainly more universe. Perhaps an enormous amount more, perhaps infinite amounts, but we can't see it. We can't know anything about it. Those regions are outside our past light cone. No signal from there has had time to reach us since the beginning of the universe. They're causally disconnected from us, as surely as if they didn't exist. And it gets stranger. The universe's expansion is accelerating. Distant galaxies are receding from us faster and faster. Some galaxies are now receding faster than light. Not because they're moving through space faster than light, which would violate causality, but because space itself is expanding so quickly that the distance between us grows faster than light can cross it. These galaxies are leaving our observable universe. Light from them will never reach us, no matter how long we wait. They're crossing over our cosmic horizon, disappearing from any possible future observation. In the far future, if the acceleration continues, more and more galaxies will vanish beyond this horizon. The observable universe will shrink in contents, even as space continues to expand. This is the ultimate consequence of spacetime's causal structure combined with cosmic expansion. Information is irretrievably lost. Knowledge becomes impossible. Regions of the universe that were once visible become forever inaccessible. The light cones that define what we can know are being squeezed by the expansion of space itself. What about attempts to circumvent these causal limits? What about wormholes, those tunnels through space-time that science fiction loves so much? Wormholes are valid solutions to Einstein's field equations. The basic idea is that space-time could have a topology like a bent tube connecting two distant regions. Enter one mouth of the wormhole, travel through the tunnel, and emerge from the other mouth somewhere far away. Maybe in another galaxy. Maybe in another time. The problems with wormholes are severe. To keep a wormhole open long enough to travel through, you'd need something called exotic matter. This is matter with negative energy density. Normal matter has positive energy density. It curves space-time in certain ways. Exotic matter would curve space-time in the opposite way, holding the wormhole throat open against its natural tendency to pinch shut. We don't know if exotic matter exists. Some quantum field effects can produce small amounts of effectively negative energy density under special circumstances. But whether you could gather enough exotic matter to stabilize a macroscopic wormhole is completely unknown. Most physicists are skeptical. Even if you could build a stable wormhole, there's another problem. Wormholes might be convertible into time machines. If you move one mouth of a wormhole at high speed and then bring it back, time dilation means less time passes at the moving mouth. The two mouths could end up at different times, travel through the wormhole, and you'd travel through time as well as space. This brings us back to the causality problem. If wormholes can serve as time machines, allowing travel to the past, then all the paradoxes return. The grandfather paradox, the bootstrap paradox, the logical contradictions that faster than light travel would create. Stephen Hawking proposed what he called the chronology protection conjecture. He suggested that the laws of physics conspire to prevent time travel to the past. Whenever you try to create a time machine, whether through wormholes or rotating black holes or cosmic strings or any other mechanism, something happens to stop you. Maybe the wormhole collapses. Maybe quantum effects create radiation that destroys anyone trying to travel through. Maybe the universe simply doesn't allow closed loops in time. We don't know if the chronology protection conjecture is correct. It's a conjecture, not a proven theorem. But the fact that we don't see time travelers from the future is at least weak evidence that either time travel is impossible, or time travelers are extremely good at hiding, or the future holds no one who wants to visit our particular era. Most physicists suspect the first option. Gravitational waves provide a beautiful confirmation of spacetime's causal structure. When LIGO detected gravitational waves in 2015, it wasn't just detecting ripples in spacetime, it was confirming that these ripples travel at exactly the speed of light. In 2017, LIGO and its partner detector Virgo observed gravitational waves from two neutron stars colliding. About 2 seconds later, telescopes observed a gamma-ray burst from the same location. The gravitational waves and the light traveled 130 million light-years at almost exactly the same speed. The difference, if any, was less than 1 part in a million billion. This confirms that gravitational disturbances propagate through space-time at the speed of causality, just as electromagnetic disturbances do. The causal structure of space-time is the same for gravity as for light. The light cones are the same. The speed limit is the same. Space-time enforces its rules universally. There's another deep puzzle related to black holes and causality that physicists are still grappling with. It's called the information paradox. When something falls into a black hole, it seems to disappear from the universe. The black hole's event horizon is a one-way membrane. Information about what fell in seems to be trapped behind the horizon forever. Eventually, the black hole itself will evaporate through a process called Hawking radiation. But this radiation appears to be completely random, carrying no information about what originally formed the black hole or what fell into it. This creates a problem. Quantum mechanics says information can never be destroyed, but black hole evaporation seems to destroy information. Something has to give. Most physicists now believe the information somehow escapes, encoded in subtle correlations in the Hawking radiation, but exactly how this works remains mysterious. It involves the intersection of quantum mechanics and gravity, which we don't yet fully understand. The resolution, whatever it is, will tell us something deep about the nature of causality and information in space-time. What space-time permits and forbids ultimately comes down to light cones and causal structure. You can send signals and influences into your future light cone. You can receive signals and influences from your past light cone, but you cannot interact with events outside your light cones. The space-like separated region where cause and effect are not defined remains forever beyond reach. This structure preserves causality. It ensures that causes precede effects, at least for causally connected events. It prevents the logical paradoxes that faster-than-light communication would create. It makes science possible. It makes prediction possible. It makes the universe comprehensible. We take this order for granted. We assume that causes precede effects, that the past is fixed while the future is open, that time flows in one direction. But these aren't arbitrary features of reality. They emerge from space-time's structure. A universe with different space-time geometry might have different causal properties. Effects might precede causes. Time might flow in multiple directions or no direction at all. The orderly sequence of events we experience might dissolve into chaos. Space-time is the enforcer of causality, the structure that makes cause and effect meaningful. Without it, logic wouldn't work. Effects could precede causes. Events could influence their own pasts. The orderly flow of time, where cause leads to effect, leads to further effects, would dissolve into chaos. We're fortunate that our space-time has the geometry it does, a geometry that supports logic, that enables science, that allows complex structures, including living creatures, to develop and persist. Space-time's causal structure isn't just an abstract property of physics. It's part of what makes existence possible, part of what makes us possible. We've explored what space-time is. We've seen how space and time are unified into a single four-dimensional fabric. We've discovered how mass and energy curve this fabric, creating what we experience as gravity. We've examined the causal structure of space-time, the light cones that determine what can influence what, the cosmic speed limit that preserves cause and effect. Now let's ask a different kind of question. What does all of this mean? What does it mean to live in space-time? What does our understanding of space-time tell us about reality, about time, about the future, and about ourselves? Let's start with a fact that sounds impossible, but is absolutely true. You are always moving through space-time at the speed of light. This seems paradoxical. You're sitting still right now, perhaps, watching or listening. How can you possibly be moving at 300,000 kilometers per second? You don't feel like you're moving that fast. You don't see the world blurring past. Everything seems stationary, but here's the key insight. Motion through space-time includes motion through time, not just motion through space. When we talk about moving through space-time, we're not just talking about moving left or right, forward or backward, up or down. We're talking about moving through the time dimension as well. When you're sitting still spatially, when you're not moving through space at all, you're moving entirely through time. Your world line, your path through space-time, points straight into the future. All of your space-time velocity, all of your motion through the four-dimensional fabric is allocated to the time dimension. You're racing through time at the speed of light. Now think about what happens when you start moving through space. You get up and walk across the room, you drive your car down the highway, you fly in an airplane across the country. When you move through space, some of your space-time velocity shifts from the time dimension into the spatial dimensions. You're now moving partly through space and partly through time, rather than entirely through time. This is the deep reason behind time dilation. If you're moving through space, you have less velocity available for moving through time. Your progress through time slows down. Time passes more slowly for you compared to someone who's stationary. The total magnitude of your velocity through space-time is always the same, always the speed of light. It's a constant. What changes is how that constant velocity is distributed between space and time. When you're stationary, it's all in time. When you're moving spatially, some shifts to space and less remains for time. At everyday speeds, this redistribution is negligible. If you're walking at 5 kilometers per hour, the amount of space-time velocity shifting from time to space is incredibly tiny. Time passes essentially normally for you. The effect is there, but it's far too small to measure with ordinary instruments. But at relativistic speeds approaching the speed of light, the shift becomes dramatic. If you're traveling at 95% of light speed, a large fraction of your space-time velocity is now in the spatial direction. Much less remains for time. Your clocks run at about 1/3 their normal rate compared to stationary observers. If you could somehow travel at exactly the speed of light, all your space-time velocity would be in the spatial direction. Nothing would be left for time. From the perspective of a photon traveling at light speed, no time passes at all. The photon's journey from a distant star to your eye, a journey that takes years from your perspective, takes 0 time from the photon's perspective. For a photon, emission and absorption are the same moment. This is why massless particles like photons always travel at the speed of light. They have no choice. They have no option to trade spatial velocity for temporal velocity. They must move entirely through space, with nothing left over for time. Traveling at light speed isn't something photons achieve. It's something they're constrained to do by the structure of space-time itself. This perspective gives you an intuitive sense of what space-time really is. It's the medium through which all existence travels. Everything is moving through space-time at the same total speed. The only difference is the direction. Stationary objects move through time, fast-moving objects move partly through space, photons move entirely through space, but the total speed through space-time is always the same. Now, let's consider a philosophical implication of space-time that has generated enormous debate among physicists and philosophers: the block universe. In our everyday experience, the past is fixed. It's already happened. We have memories of it. We can't change it. The future, by contrast, is open. It hasn't happened yet. It's undetermined. We're about to create it through our choices and actions. And the present is the knife edge between them. The moment of now, the constantly advancing boundary separating what has been from what will be. This feels deeply, obviously true. The past is gone. The future doesn't exist yet. Only the present is real. But in space-time, things look very different. Space-time is four-dimensional. All events have positions in it. The explosion of a firecracker yesterday has coordinates in space-time. The explosion of a firecracker tomorrow also has coordinates in space-time. Both events exist as points in the four-dimensional structure. Both have definite locations in the fabric of reality. From this perspective, space-time is like a static block, a frozen four-dimensional sculpture containing all of history. Everything that has ever happened and everything that will ever happen is already there, laid out in the four-dimensional geometry. The past isn't gone. The future isn't unwritten. They're just in different locations along the time axis. This view is called the block universe, or sometimes eternalism, and it raises profound questions about the nature of time, change, existence, and free will. In the block universe, there's no objective present moment, no special now that divides past from future. Remember what we learned about the relativity of simultaneity. What counts as now depends on how you're moving. Different observers have different definitions of the present. Events that you consider simultaneous, happening at the same time, another observer might consider sequential, happening at different times. There's no cosmic clock ticking away that everyone agrees on. No universal present moment that's the same for all observers. Different observers have different now slices through space-time. And according to relativity, none of these slices is more correct than any other. They're all equally valid ways of carving up space-time. So there's no objective now. No privileged present moment that's more real than other moments. If that's true, and if the past and future are just different regions of the same space-time block, then in what sense does time flow? In what sense do things change? Some physicists and philosophers take the block universe completely literally. They argue that time doesn't actually flow. Change is an illusion. Nothing really happens. Everything just is, statically arranged in the four-dimensional block. Our sense of time passing, our feeling that the future is becoming present and then becoming past, is a feature of our consciousness, not a feature of reality itself. We're experiencing different parts of the block sequentially, but all the parts exist equally. Others resist this conclusion. They argue that the block universe is a mathematical representation of reality, but that mathematical representations don't capture everything important. They say the experience of time passing is real, genuine, not an illusion. That's something like presentism. The view that only the present moment truly exists might still be defensible even if the equations of physics don't seem to support it. This debate is ongoing. There's no scientific consensus. The block universe is what the equations of relativity seem to describe. But whether the equations capture everything important about time, whether they tell the whole story, remains unclear. Let me give you a sense of how strange the block universe really is. Imagine your entire life as a four-dimensional pattern. Your birth at one end, your death at the other. Every moment you've ever lived, every experience you've ever had, strung out along the time axis of space-time. In the block universe, all these moments exist eternally. The you from yesterday didn't cease to exist when today arrived. That version of you is still there, at that position in space-time, still having those experiences, still thinking those thoughts. So is the you from 10 years ago, the you from childhood, every version of you that has ever existed. And here's the strange part. The you of tomorrow is also there. The you of next year. The you of decades from now. Those versions of you already exist in the block. Your future is, in some sense, already there. Already laid out. Already part of the eternal four-dimensional pattern. Your life isn't a sequence of moments that appear and then disappear. It's a static pattern in space-time, a world line, a curve through the four-dimensional block. The pattern is eternal. It doesn't change. What changes, if anything does, is which part of the pattern your consciousness is currently experiencing. This raises difficult questions about free will. If the future already exists, are your choices real? Or are they just the unfolding of a pattern that was always there? When you deliberate about what to do, weigh options, make decisions, is that genuine choice? Or is it just your experience of a predetermined world line? Some philosophers argue that free will is compatible with the block universe. Your choices are real in the sense that they're genuinely part of the pattern. They weren't imposed from outside. They emerged from your own deliberations, your own character, your own desires. You couldn't have chosen differently because what you chose is what's in the block. But the choice was still yours. It was still you choosing. Others find this unsatisfying. They argue that genuine free will requires an open future, a future that doesn't exist yet and could go different ways depending on what you choose. The block universe seems to preclude this kind of openness. If the future already exists, then in what sense can your choices affect it? There's another deep connection here that physicists are still exploring: the relationship between the direction of time and the increase of entropy. Entropy is a measure of disorder. The second law of thermodynamics says that entropy in a closed system always increases or stays the same. It never decreases. A room gets messier over time, not cleaner. An ice cube melts in warm water. Perfume spreads through a room. These processes happen in one direction only. This gives time an arrow, a direction. We remember the past, not the future. Causes precede effects. Eggs break but don't unbreak. The increase of entropy distinguishes past from future in a way that the fundamental laws of physics don't seem to. The fundamental equations of physics are mostly time-symmetric. They work equally well, forward and backward. If you film a collision between two billiard balls and play the film backward, the reversed motion is just as physically valid as the original. The equations don't prefer one direction over the other. Yet the world we experience has a clear arrow of time. We age. We remember yesterday, but not tomorrow. The universe began in a state of low entropy at the Big Bang, and has been getting more disordered ever since. Why should there be this asymmetry when the fundamental laws are symmetric? This question connects to the block universe in interesting ways. If all moments exist equally in the block, why does our experience have a direction? Why does consciousness seem to move from past to future rather than future to past? Why do we experience time passing at all? Some physicists suggest that our experience of time's flow is connected to how information and memory work. We form memories of events, and those memories take time to form. The direction of memory formation, from present to past, might be what creates our sense of time flowing from past to future. But this pushes the question back rather than answering it. Why do memories form in one direction and not the other? These questions remain open. The relationship between the physics of space-time, the thermodynamics of entropy, and the phenomenology of experienced time is still not fully understood. The block universe describes the structure of space-time, but it doesn't obviously explain why we experience time the way we do. Let's consider the practical reality of gravitational time dilation and what it means for actually traveling through time. We discussed in part 2 how time runs slower in stronger gravitational fields. Your head ages faster than your feet because it's slightly farther from Earth's center, slightly higher in the gravitational field where time runs faster. The difference is tiny, about 10 billionths of a second per year for a 2-meter height difference, completely undetectable in everyday life. But it's real. This effect becomes significant in extreme gravitational fields. Near a black hole, time slows dramatically. If you could somehow hover near the event horizon of a black hole and then return to Earth, you'd find that much more time had passed on Earth than for you. While you experienced a few years, Earth might have experienced centuries or millennia. This is time travel. Real, genuine time travel into the future. Not the science fiction kind with a machine that zaps you forward, but a physical phenomenon, a consequence of space-time geometry that allows you to reach the future while aging less than everyone else. The extreme version would be to orbit close to a black hole, skimming near the event horizon where time dilation is most severe. Spend a year of your subjective time in that extreme gravity well, and you might emerge to find thousands of years have passed elsewhere. You'd step out of your spacecraft into a future you can barely imagine. Civilizations might have risen and fallen, technology might have advanced beyond recognition. Everyone you knew would be long dead. This asymmetric time dilation is one-way time travel. You can leap into the future, you can arrive at tomorrow faster than everyone else, but you can never go back. No path through space-time leads to your original time. The past is behind you, unreachable, separated from you by the inexorable geometry of space-time. Now, let's talk about one of the biggest unsolved problems in all of physics: the tension between space-time and quantum mechanics. General relativity describes space-time as smooth and continuous. It curves gently near small masses, more sharply near large masses, but it doesn't jump or jitter. It's a classical field, deterministic in its behavior, well-behaved mathematically. Given the distribution of mass and energy, you can calculate exactly how space-time curves. Quantum mechanics describes the world very differently. At small scales, everything is probabilistic. Particles don't have definite positions until you measure them. They exist in superpositions of multiple states simultaneously. Measurements collapse wave functions in unpredictable ways. Randomness is fundamental, built into the fabric of reality at the deepest level. Both theories are extraordinarily successful within their respective domains. General relativity describes gravity, space-time, and the large-scale structure of the universe. It predicts black holes and gravitational waves and the expansion of the cosmos. Quantum mechanics describes atoms, particles, chemistry, and the behavior of matter at microscopic scales. It underlies all of modern electronics, chemistry, and molecular biology. Both theories have been tested with incredible precision. Both are correct. They're among the most thoroughly verified theories in all of science. But they don't fit together. They contradict each other in fundamental ways. The smooth space-time of general relativity clashes with the jumpy, probabilistic nature of quantum mechanics. When you try to apply quantum mechanics to gravity, to treat space-time itself as a quantum system, you get infinities and contradictions. The mathematics breaks down at extremely small scales, around the Planck length of about 10 to the minus 35 meters. Both gravity and quantum effects should be important. That's about 10 to the 20th power times smaller than a proton, unimaginably tiny. But we don't know what happens there. Our theories fail. We need a quantum theory of gravity, a theory that unifies general relativity and quantum mechanics, but we don't have one. String theory is one attempt. It proposes that the fundamental constituents of reality aren't point particles but tiny vibrating strings. Different vibrations correspond to different particles. Gravity emerges naturally from the theory, but string theory requires extra dimensions of space, dimensions that we've never observed. and it makes few testable predictions. Loop quantum gravity is another attempt. It proposes that space-time itself is quantized, made of discrete chunks rather than being continuous. Space is woven from tiny loops. Time proceeds in tiny steps. The smooth space-time of general relativity emerges as an approximation at large scales. There are other approaches: causal set theory, asymptotic safety. Each takes a different path toward quantum gravity. None has been experimentally confirmed. None is clearly correct. We don't know which, if any, is on the right track. What would quantum spacetime look like? Some theories suggest spacetime is fundamentally granular. Below the Planck scale, the concept of smooth, continuous spacetime might break down entirely. Space might become foamy, fluctuating, uncertain. Distance and duration might lose their meaning. Some theories suggest that space-time itself might emerge from something deeper, that what we perceive as four-dimensional space-time is not fundamental but arises from more basic quantum entities. Entanglement between quantum systems might create the illusion of spatial connection. Information might be more fundamental than space. These are radical ideas that challenge our basic intuitions about reality. How might quantum mechanics modify the block universe picture? This is speculative territory, but there are interesting possibilities. In standard quantum mechanics, before a measurement, a system exists in a superposition of multiple states. Only when you measure does the system collapse into a definite state. If you apply this to the universe as a whole, you might imagine that the future isn't fully determined. The block isn't complete. Future portions of spacetime exist only as superpositions of possibilities, collapsing into definiteness only as time passes. This might rescue free will from the determinism of the classical block universe. Your choices might genuinely be open, with multiple possible futures existing in superposition until your choice collapses them into one actual future. The block universe would still exist, but it would be built up moment by moment rather than existing all at once. But this interpretation has problems. What counts as a measurement? When does collapse happen? These questions are already controversial in ordinary quantum mechanics. Applying them to the structure of space-time makes them even harder. The point is that our understanding of space-time is incomplete. General relativity is incredibly successful, but it's probably not the final word. Somewhere, at some scale, the smooth four-dimensional space-time of Einstein gives way to something else, something stranger, something we haven't yet discovered. What that something is remains one of the great mysteries of physics. Let me close by reflecting on what it truly means to understand space-time, because understanding space-time changes how you see everything. You look up at the night sky, you see stars scattered across the darkness, points of light, some bright, some dim, arranged in patterns we call constellations. But you now know what you're really seeing. Light from those stars has been traveling through space-time for years, decades, centuries, millennia to reach your eyes. A photon that left a distant star 1,000 years ago has been tracing a geodesic through curved space-time ever since, finally arriving at your retina tonight. That light carries information about events in the past. The stars you see aren't as they are right now. They're as they were when the light left them. Looking at the sky is looking backward in time, seeing the past preserved in photons that have crossed the vast distances of space. But in the block universe perspective, it's not really the past in the sense of something that's gone. It's just a different region of space-time. Those events, the emission of light from those distant stars, exist in space-time just as much as events happening around you right now. They're in different locations along the time axis, but they're equally real, equally part of the four-dimensional structure. This is disorienting. It challenges our deepest intuitions about time and change and choice, but it's also oddly liberating. Your past, those moments you regret or treasure, they're not gone. They're still there in space-time, part of the eternal pattern of your world line. The you who experienced your happiest moments is still there, at those coordinates in space-time, still having those experiences. The you who struggled through difficult times is still there too, still learning, still growing. Nothing is lost. The loved ones you've lost, their world lines intersected yours for a time. Those intersections, those shared moments, are permanent features of space-time. They don't disappear, they don't fade away. They're woven into the block universe forever. The people are gone in the sense that their world lines no longer run parallel to yours, but the time you shared exists eternally in the four-dimensional structure. Space-time gives a strange kind of immortality. Not personal immortality in the sense of continuing forever into the future, experiencing an endless sequence of new moments, but pattern immortality. The pattern of your existence, from birth to death, is woven into the fabric of space-time. It's part of the eternal four-dimensional structure. It doesn't disappear when you die. It doesn't get erased. The pattern is there, complete. A permanent part of reality. Understanding space-time also changes how you see the present moment. That sense of now, of the present being special and unique, is partly an illusion. Every moment feels like now to whoever is experiencing it. The you of yesterday felt that yesterday was now. The you of tomorrow will feel that tomorrow is now. Every conscious being, at every moment of their existence, experiences that moment as the present. The sense of nowness is universal to all moments, not special to this particular one. This moment doesn't have any objective property that makes it the real present, while other moments are mere past or future. It just feels like the present because you're experiencing it. And yet, you are here. You are experiencing this moment. That experience is real, even if the block universe is correct. Even if past and future exist equally, your subjective experience of this moment is happening. Consciousness, whatever it ultimately is, traces world lines through space-time, and your world line is real. Living in space-time means accepting limits. The speed of light is a genuine constraint on what's possible. The stars are genuinely far away, separated from us by years and centuries and millennia of light travel time. The universe is genuinely old and vast, stretching billions of light years in every direction and existing for billions of years before we arrived. We can't just decide to travel faster than light. We can't communicate backward in time. We can't reach distant galaxies in human lifetimes without accepting that centuries or millennia will pass on Earth while we travel. These aren't engineering problems that future technology might solve. They're structural features of reality, woven into the geometry of space-time itself. But within those limits, enormous richness is possible. We can explore, we can understand, we can ask questions about the nature of space-time and get meaningful answers. We can build telescopes that see light from the early universe. We can build detectors that feel gravitational waves from colliding black holes. We can develop theories that explain the curvature of space-time and the structure of causality. That's remarkable. The universe doesn't owe us comprehensibility. There's no guarantee that finite creatures like us, evolved on a small planet around an ordinary star, should be able to understand the fundamental structure of reality. And yet, here we are, grasping at the deepest truths, comprehending space-time, understanding our place in the four-dimensional fabric of existence. Space-time is the arena of all existence. Every thought you've ever had occurred at some location in space-time. Every historical event has coordinates in the four-dimensional structure. Every star, every galaxy, every black hole, every atom exists within this fabric. It curves and bends in response to matter and energy. It permits and forbids according to its causal structure. It enforces the rules that make physics and logic possible, and you are in it. Your world line threads through space-time from your beginning to your end. You're not outside space-time looking in. You're not separate from it. You're part of it. Part of the fabric. Part of the structure. A pattern woven into the four-dimensional geometry. The stars you see above aren't in some separate space disconnected from you. They share your space-time. The light connecting you to them traces geodesics through the common fabric. The gravitational waves rippling from merging black holes billions of light years away are distortions in the same space-time you occupy. Everything is connected through this single, unified structure. This is what space-time actually is. Not an abstraction, not a mathematical convenience, not a coordinate system for describing where and when things happen. The actual fabric of reality itself. The structure underlying everything we see and experience and know. The stage on which the universe performs its endless drama. And you are both audience and actor. Watching and participating, observing and existing, trying to understand the structure even as you're embedded within it. That's the strange and wonderful situation of conscious beings in space-time. We're part of what we're studying. We're made of what we're trying to understand. The next time you look up at the stars, remember what you've learned. The light traveling from those distant suns to your eyes is tracing geodesics through curved space-time. The time passing as you watch is your motion through the temporal dimension. The gravity holding you to the ground is the curvature of space-time telling your body how to move. Space-time is everywhere. Space-time is everything. And now you understand, at least a little better, what space-time actually is. Thank you for joining me on this journey through the fundamental nature of reality. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep explorations of the cosmos and our place within it. Good night. And may you never see the universe the same way again.